All right, guys. So let's do the notes. Okay, so these are going to look just like your notes that you have on your student slides. They're not really fancy looking. They're just the bare text. Okay, Maggie. They're just the bare texts, and nothing too crazy. Oh wait, sorry, go back. So you do have classwork 3 today, which you do have on your tables. You just got to, fill them in. Yes, this is Magneto. Yep, so classwork 3. Homework 4, of course. It's not going to be due. I fixed that. It's going to be due day 4. It is right. I did fix it. So it's due day 4 instead of day 5 now. So it's going to be a little shift. We're going to do what was going to be day 4 on day 3 and day 3 and day 4 because I'm out on Monday. So it's going to mess everything out. So it's kind of yay. Yeah. So there's the notes. Magneto, you've not been up here the entire time, and then as soon as I start talking, you're like, hey, can I be part of this? Okay, fine. Be part of this. Okay. All right, so a little bit of cat notes for you guys. Yeah. Yes, I know, Maggie. You know Buggy Boy. All right. So, objective for today. We're going to look at Molar volume. It's a new conversion factor, but we're not going to really use it as much, but it is a new one. Discover ideal gases versus real gases, learn how to use ideal gas law, and use ideal gas law for the applications like molar mass and for density. Yeah. All right, Maggie, I'm going to have you go because I'm sure you're very distracting for some folks. You gonna say bye? Say bye, everybody. Yeah? Yeah? You can see he hates me. Do you hate me? All right, big boy, come on. Or just maybe stay on my lap. That'd be better. Can you stay on my lap? Can you just stay there? Ugh. Egyptian mouths, I swear. Okay, so let's take a look. Avogadro's principle. Oh, by the way, since I'm going to talk about the notes, maybe it might be good to have the notes up on the screen. You don't have to have my video on your face, maybe just the audio. And you can be looking at the notes or writing notes down, or you could just sit back and listen because you can do this multiple times. Yeah, so there's that. So kinetic molecular theory, and we talked about that. Basically, the size of the particles, making how they move. Essentially, very large krypton particles occupy about the same amount of volume as helium particles because there's so much empty space between those particles. So if I have a big old bag of any gas, and it's the same pressure and temperature, they're pretty much the same amount of particles inside. And that's what Avogadro figured out, and that's what got him to understand that number that he produced that he didn't get credit for until after he died. It was all because of gases. He was exploring gases. So if you look at some different gases like helium, oxygen, carbon dioxide, I could have the same size container, same pressure, same temperature, and I have inside the same number of particles. Because they're that tiny, it doesn't really make much difference about the size of the particle changing the amount that's in there. It's kind of cool, actually. So 6.02 times 10 to the 23rd particles is what you get, right? So the molar volume of any gas, 1 mole of it, right, is going to have 6.02 times 10 to the 23rd particles in it. Because 1 mole of anything is 6.02 times 10 to the 23rd, right? It's just what you got, right? Cool. Okay. So, standard temperature and pressure. So we had to have a standard temperature and pressure to have the point where we have everything kind of focused on one area. And what it boils down to is 0 degrees Celsius, right? At 1 atmosphere or close to, which we actually now the official STP is 100 kPa. So 100 kilopascals, so pretty much 1 atmosphere, because 1 atmosphere is about 101.2 kilopascals. So very close. And you can see it's a whole International Union of Pure and Applied Chemistry, the IUPAC standard, 0 degrees, 100 kilopascals, right? And that makes because we're using kilopascals and we're using 0 degrees Celsius, that makes the liters per mole 22.7. But if you were to like look at old textbooks or watch some other videos, you might see some other sources say 22.4 liters per mole, but that's because they're using STP as a standard of 1 atmosphere and 0 degrees Celsius. And so that little itty bitty change, that little bitty change in definition shifted to 22.7 to 22.4 to 22.7. So from this point forth, because this is the official number per the textbook makers, per the IUPAC, is 22.7 liters per mole. So that's what we're going to do. Okay? So try to remember that. Now your numbers won't get too far off of you, 22.4, but you can see why there's a little bit of difference. Because one was atmospheres, this is kilopascals. Okay? So as you can see, you know, STP, IUPC, 100 kilopascals, that's what you all can, kind of look forward to. Now, the National Institute of Standards and Technology, or NIST, defines it as being 0 degrees in 1 atmosphere, and that's why you'll see 22.4. So everything I just kind of said, but we're going to go with 22.7 because that's the official standard. Yeah. So 1 atmosphere, of course, equals about 101.3 kilopascals, slightly higher than 100 kilopascal, and that's why there's the very slight difference. So we're going to basically use the IUPAC version, not the NIST version. Okay, so moving forward, so Avogadro's principle and molar volume can be extremely helpful in solving ideal gases. I'm going to talk about ideal gases in a second. So just kind of put a pin in your head on that one. So, for example, if you have a gas that's 3.72 liters, right, and it's a STP, so that means it's at 0 degrees Celsius, 100 kilopascals. So remember, STP is standard temperature pressure. You can figure out that 1 mole of that is 0.164 moles. That's a pretty easy calculation. You're just dividing the liters you're given by the 22.7, and you got how many moles you have. Pretty nice. Yeah. All right. So the ideal gas law uses this concept to bring together the Boyle's, the Charles, and Gay-Lussac's law and the ideas of kinetic molecular theory to help us understand the amounts of the substance. So this helps us to get the amounts, which is kind of cool. It's a really interesting application. They all kind of just come together. So if you look at the combined gas law, how it's got like P1V1 over T1 equals P2. If I take one side and make it a constant, a thing that doesn't change in nature, so everything kind of equals this one primary equality, right? Make it equal to a constant. Well, then that constant can give me a relationship eventually where I can add the number of it. So n becomes a new variable that you're going to solve for in these problems, and n is moles. I know it's like, but why don't we use m? Because m is used for so many things in science, like mass and meters. So we use n for moles. Okay, so n is the amount, and of course there's this constant. We need a constant letter, so we use r. So now that constant, where it says constant, that actually equals something. That becomes a number. And you can see here's some values of r. Now, it all depends on what are my units. Is it liters in kilopascals, moles in Kelvin? Well, then it's 8.314. Am I liters in atmospheres? Well, then 0.821. Am I using millimeters of mercury? Well, then it's 62.4. And these are all rounded. So if I'm using, like say if I use the bottom one, right? Or the bottom two, those are 3 sig figs each. So that will affect the precision of my answer. Whereas the top one is 4 sig figs, so that will be a little more precise probably using calculations. So it depends on what is my pressure. Is my pressure kilopascals? Is it atmospheres? Or is it millimeters of mercury? Or torr, because it's the same thing, right? Yeah, so that's kind of the things you're looking for here. So here is, PV equals nRT. That is the ideal gas law. That's something that's been sitting on the wall in my classroom for a while now. If you will look over, you probably see it sitting there. So ideal gas law, PV equals nRT. You're basically plugging in these things. You're solving for the missing variable. I might try to find for pressure, for volume, for temperature, or for the amount of the gas, which is the N. Right? We're not going to solve for R. You're going to use R from that chart or one that's on your help page. It's a little more. There's a lot more on that one. So that's a good one to use. But yeah. So that's really all it boils down to. Temperature's got to be in Kelvin, N's got to be in moles, Now, it doesn't matter what the pressure and volume is as long as it matches your R constant. So if you're using milliliters, but your R constant has liters on it, well, then you better convert your volume to liters because they have to match the constant. If they don't match the constant, you're not going to get the right answer. So that's, we just got to choose, but choose wisely. Okay? Choose wisely. I'm getting sleepy because it's after midnight and I'm making this for you guys. Yeah, so ideal gas law, right? P represents volume, V represents, P pressure, V volume, N moles, R ideal gas constant, T temperature, temperature in Kelvin, right? All that says right there. Yeah, so basically, you can actually use this to figure out other things as well. So because now we have moles and we have volume, we can actually figure out mass. We can figure out density. So we can use this stuff to figure out the density of a gas. So if we didn't know the density of a gas, but we knew that all gases contain the same amount in a certain specific volume and temperature, then I could actually figure out what is the density of that gas. And you know what? This is how they figured out the density of many gases as we discovered them before we had better ways to measure those densities. It was done in this manner. So don't stress out. It does look a little bit more interesting. Just remember that the big M is the molar mass and the little m is actual mass, like how many grams of my substance, right? So N is moles, and moles, can be equal to the amount of mass per molar mass. Remember, because molar mass is grams per mole. So we can kind of plug it in as M over M, and you can kind of rearrange it algebraically, kind of just move it around, divide both sides by the same thing, and we end up getting this nice little thing here at the bottom, which is the big M, which is molar mass, is equal to the mass of my gas times the gas constant times temperature divided by the pressure times volume. But make sure you put your stuff in parentheses before you hit that divide button for PV, because order of operations matters. Yeah. So it's not horrible. It just looks a little weird. But as long as you recognize that whole molar mass is grams per mole, and then that's what I have right here, literally grams per mole, molar mass, it's kind of like that, right? It works. It plugs in. It's beautiful. Yeah, it's like different equations all coming together, all right? And, trying to find density, density is literally mass over volume. So if I've got mass and volume in my formula, well, guys, that's density. So I can literally just take that out, make it density, and then do some more finagling, and I can find out the density of my gas. If I had the molar mass of my substance, and I know the pressure of it, I know the temperature of it, and the constant I'm using, I can find my density. Yeah. So that's what you. We're not going to do a lot of those, but you just want to know that there's applications of this ideal gas law. It's not just solving for temperature, solving for pressure and volume. There's actually higher order thinking here that we can actually use it to, figure out different kinds of systems of study. So ideal gas law and density help us explain hot air balloons and how they fly, right? You fill them first with cold air that has the same density as the outside, so it's nice and filled up. And then we heat the air inside. It gets all hot. And when it gets all hot, the particles move faster and the pressure goes up. And basically, some are forced out, but the decrease in the amount of gas inside. But the thing is that the density inside the balloon drops. And when the density inside the balloon drops, it's now lighter on the inside than it is on the outside, so it floats. Just like a big gas bubble in the water floats upward and eventually pops to the surface. But a hot air balloon kind of acts like that bubble going through the air. It just has a low density inside because you've heated it up. That's why you see that fire shooting into the middle of that balloon, because it's making it go up. And so the density thing, that's what's happening to that balloon. So it's kind of cool, right? And you can kind of see where the ideal gas law is related to the other gas laws. So they all kind of do this, right? There's a lot of handshaking going on here. You can kind of see if I do my thing and I make them equal to NR and NRP, and eventually it's the same thing. This is, Charles's Charles's law here, right? You can do the same thing with Gay-Lussac's law and Boyle's law. They all kind of just come together like that, right? So on this slideshow, this source slides, they had stuff that was red. Anything you saw red were quantities that didn't really change. They kind of existed. Everything else kind of fluctuated around them, right? So if you went back and looked at some of the prior slides, you would see that. And it is kind of interesting how they are. I might keep that on the final slides. I don't know. But for right now, this is what we have on these. Like I said, I pulled a lot of this from the textbook stuff. Yeah. This is like the step before I go and I make everything look prettier and make it look like I do on my Canva thing. This is kind of like the rough draft. Sorry, guys. I know. Nice thing is that it follows perfectly what's with the textbook. So if you go back and read the third section, read the book, you would find that this stuff follows right along with it. It goes right perfect. So I suggest it. I'm telling y'all, take a minute in your life, read a few pages, be like, oh, this isn't that bad. They actually wrote it pretty nice. Yeah. Real versus ideal gases. There are different kinds of the different concepts. Actually, one is a mythical, possible, imaginary version of gas, and one is what we really see. Thing is, though, what we really see is pretty much like the imaginary version. It's just, sometimes reality isn't perfect. Engineers get really picky about, ideal gas law, because they're like, there's really no such thing as an ideal gas, and like you should hear them like go off about it. It's quite interesting. Yeah, they do. But yeah, so we got to kind of imagine, so what is going on here? So kinetic molecular theory defines properties of an ideal gas as a particle with zero volume. So no volume. What? How does a particle have no volume? Does it not exist? So we're pretending it's so small that there's no volume. That should be an alarm bell, right? But we have to for the math. Particles experience no intermolecular attractive or electrical forces. They're not like statically charged on each other. They're not on gravity. There's not whatever. It's just we're pretending they don't. There's no interaction. They're not attracted or repelled by the container. But the container has mass, right? It doesn't have gravity. Well, the thing is, it's such a small, minuscule attraction that we can basically say, nah, not there, and it works. The math still works fine without it. And then the particles in constant random motion. Are they always random, or is it kind of like they hit a certain perfect angle, they're just going to ricochet off? And it's kind of subjective, right? So, but we're going to say they're in constant random motion, and they move in straight lines until they collide. But doesn't gravity cause things to curve around space-time? So you can kind of see already from our definitions of what a ideal gas is, there is some hiccups here. But the thing is, they're such small, little itty-bitty deviations that in reality, they do not make a big difference when I'm looking at a great big system of gas. It just doesn't change all that much, right? Right, so collisions being perfectly elastic. I told you, imagine two cars that collide, just bounce off like nothing ever happened. That's how we're imagining these gases, right? The kinetic energy doesn't change. The whole system has the same amount of energy because it's just constantly in motion. Blah, 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 blah. It's how we have to define it to make this work. Otherwise, we'd have this great big gaping hole in the middle of our laws, and we wouldn't be able to build rockets to go to space and everything else. We had to find a way to make it work, and it works. It just works. And the gas constant is part of that. The gas constant is how we kind of make up for a little bit of that in the middle there. But it works. And that's why these problems make sense. That's why we can use them for real science and medicine and space travel and jets and all the stuff that gases are really needed for, right? I mean, you're drilling for natural gas, you got to account for the pressure coming out of the earth and be able to predict the amount of it moving through the lines. There's a lot of applications of all this. So much. It's where it all goes. And the KM theory has a lot of assumptions and simplifications. So there's a lot of things that are, you got to take with a grain of salt here. So right now we're going to say these are how they are, but if you go into higher order levels of science in the future, say you want to be an engineer, you're probably going to learn that this is kind of like the surface and there's stuff going on underneath. You're going to learn a bit deeper. So right now, just kind of this is why we're telling you about the difference between real and ideal and what that is. So read through it very carefully and think about this a little bit. All right. So real gases deviate from ideal gases at very low temperatures and high pressures. So if I have a medial temperature and pressure, my stuff acts like a perfectly ideal gas. There's no problems, everything's great. But it's when I put it at very low temperatures and very high pressures is when I start seeing these kind of rules breaking down, like that kinetic energy thing becomes all skew, slower particles have more time to interact, right? If it's low enough, nitrogen condenses to form a liquid. So like gases becoming liquids. So a high pressure of carbon dioxide is a liquid at a certain temperature. But at like this pressure, if I make carbon dioxide at a certain temperature, it's going to go straight from a gas to a solid with no liquid state. But add enough pressure to it, and then the whole real versus ideal gas thing begins to kind of get a little cloudy. It's like propane and propane accessories. Under high pressure, under regular pressure, it's like a real gas. But as soon as I put high pressure on it and they get close together, it turns into a liquid. Which is why if you get a propane tank and you fill it up and you shake it, you're gonna hear liquid inside. It's a liquid inside that sucker because it's got so much pressure in it that when pressurized, it got really cold, it becomes liquid, and we can store it longer in a liquid form than we can, say, in a gas form. Plus, we can get more of it in there. And that's why propane tanks are like they are, because they're actually stored as liquid inside. You might even see it say like liquid propane or LP on the side. That's what they're trying to tell you, right? But in the minute I crack the thing out, it's gas coming out, right? Because it's so much hotter outside than it is inside that tank. And here you can kind of see like a little bit of the, as I pressurize it, the particles get close together, they start to act like liquid. And that's what they're trying to tell you here with this little image thing. Then we get the polarity and particle size, right? The charges of different things. So oppositely charged ends of a polar gas, so like water vapor is very polar. So water vapor, not really a good ideal gas, is a terrible ideal gas. It's a very strict window where you can treat water vapor as a ideal gas. But like, propane, not so great, but like methane's pretty good. It's pretty, pretty unilateral. Helium, of course, is just one particle, so it's really good to use for this. Size and particles. And here you've got like, water and like a steam, and then like a non-polar gas, like you've got helium inside a balloon. They're going to do different things in different gas states. It's going to act a little different. And guess what? That's it. That's your notes. So I highly suggest you read the third section in your textbook. Because next time on next class we're going to do the lab that we were supposed to do today. But the time after that, it's going to be gas stoichiometry. Yeah. So, all right. I hope this is good. Hope it works. If you have any questions, come see me, tomorrow morning. I'm here early, also early on Wednesday. So, it's gonna be good. You'll be all right, I promise. All right, I'm gonna make a video now about the classwork, and then once you watch the video and you put the stuff down on your classwork, then you can work together in your pairs or your trios and get the classwork done. And hopefully you walk out today with time to work on your homework, and just like you did today, maybe get all the stuff done, all of it, and go on. All right, I'm sorry I'm not there today. I had to go take care of something. Probably as you are doing this, I'm in San Antonio. So, yeah, I will be looking on at you, making you all good. All right, guys, good luck. Help each other. Be good. All right, see you guys. Oh, watch the second video before you do the classwork, because I'm going to work some of the problems.